In this video we're going to do some linear algebra, by which I mean finding determinants and inverses of matrices, solving linear equations, finding eigenvalues and eigenvectors, that sort of thing. So for that, well, as usual, we need to import numpy. But that's actually not enough. We also need to something that's kind of hangs off numpy. We have to do numpy.linalg, which we're going to import as LA. Okay, so yeah. So let's let I be the 3x3 identity matrix, and let's have some yeah, make a matrix like this. Okay, so A is going to be the matrix, 3x3 matrix with entries 1 up to 9. So let's maybe say if we wanted to do a slicker version, then we could do np.arange 1, 10. And that gives us numbers 1 up to 9, and then we can reshape it. So that's kind of a slicker way to make this matrix A, but let's not worry about that. Okay, so let's try and calculate the determinants. So determinant of the identity is 1. Determinant of A is 0. Let's just think a minute about that, remind ourselves some stuff about linear algebra. If you think about it, if we take the first row and add the last row, then you're going to get 8, 10, 12. 8, 10, 12 is twice the middle row. So the sum of the first row and the last row is twice the middle row. So that means, yeah, and in fact it's also true that, I think it's true, yeah, that the sum of the first column and the last column is twice the middle column. But yeah, so if you've got a matrix in which the rows are linearly dependent, then the determinant is always 0. That's a basic fact of linear algebra. But we could, let's say, for example, we're going to take the identity matrix plus A and calculate the determinant of that. We find we get -2. So yeah, or another thing, let's look at the Van der Mon matrix. So this is going to be top row is going to be 1, 1, 1. Then the second row is going to be 2, 2, 4, 8. And third row is going to be 4, 16, 64. So that's a random matrix here. Okay, so let's try and find the inverse of this matrix. So fortunately the linear algebra package has a nice function for that, just la.inv. Okay, so let's call that maybe bi for the inverse of b. So here we go. There's the inverse. You can see it's like 2 2/3 there, -1, and then some other entries here. Okay. So let's just try and check that it actually did this all right. So remember, what's the definition of the inverse? The point is that B times B inverse should be the identity matrix. So remember the correct syntax for matrix multiplication in Python is the @ sign. So we do B at BI. and that gives us this matrix here. And notice here I've got essentially a 1 and then a 0, and then here I've got as usual these kinds of numerical calculations you're going to get some small round off errors. This should be 0, but it's actually coming out as like 3 times 10 to the minus 17. That doesn't really matter too much. See what's going on properly. It's kind of convenient if we just subtract the identity, right? So now if we subtract the identity, then all of these elements ought to be 0. Or similarly, if we do it the other way around, bi times b, so you get this here. So here we've got some errors. Some of them are positive, some of them are negatives. Let's kind of find the absolute value of the errors in here. Okay, so remember, this is we're using this universal function business. The absolute value function is universal, so I apply it to a matrix. It'll just apply it to all the entries in there. And so we could check through all these entries individually to see how big they are, but let's maybe just take the maximum of all of these. You do np.max again. This is one of these kind of universal things. It'll just take the maximum, flatten out the matrix and take the maximum of all the things there. So we see that if we take this kind of b inverse times b minus the identity, that ought to be 0. It's not precisely 0 here. But if we take the maximum of the absolute values of all the entries, it's just like 2 times 10 to the minus 15. That's just the effect of some small round-off errors. Okay, so so now let's try and do some stuff with eigenvalues. Okay, so we do la.eig. That's the function for finding eigenvalues. Apply that to b. So it kind of comes out with sort of some sort of slightly complicated form, but it'll be tidier if we do L comma U equals like this. So now so this is probably the most common way that you would consume the result of finding the eigenvalues. You do LU like so, and then L is a vector which contains the eigenvalues, and then U is a matrix in which and the columns in the matrix U should be the eigenvectors. So let's kind of check that that's worked correctly. So we want to kind of extract the various columns of the matrix U, right? So actually, let's just put in a message here. Okay, so here we've done this with a kind of format string. New thing that I think we've not done before, I put in a \n here. \n just gives me a new line. If I didn't put in the new line, then this would not be laid out in a comprehensible way. So I want to put in a new line before I show the matrix, and so that's what the \n is there is for. Okay, so here's our vector of eigenvalues, and here's the matrix whose columns are the eigenvectors. So let's just check that these eigenvectors are correct. So I want to pull out the first column here. Now if I do U0, so that's the wrong thing. You see, that's going to give me the first row. Okay. But if, so that means the things in there. But if I do kind of colon comma 0, so what's that mean? That means kind of anything in the vertical direction and 0 in the horizontal direction. The colon just kind of means any of the possible indices. So here what I've got is this, if you check it, that's just the same thing as this first column here. So I think we're probably okay leaving that as a row vector. So that's supposed to be an eigenvector. That means that if I take b and multiply it by u0, so that gives me this thing here, and that's supposed to be the same as the corresponding eigenvalue okay. And you can see that seems to be correct, right? I mean, here matrix B multiplied by our vector u0 is yeah, that's this thing here, minus 1.13, minus 8.48, etc. And you check that that's the same thing as L0 times u0. If we wanted to kind of check this maybe a little bit more easily, it would be better if we just subtract these things. Okay. You can do np.norm. Maybe I did that. I forget the correct syntax for that, so let's not bother with it. Let's just do. Okay, we do np.abs. So to take the absolute value, and then if we do np.max. Okay, so we can see that we do bu0 minus lambda naught u0, then that's going to be the same. That's going to be 0 more or less. So indeed, this is an eigenvector, and yeah, we could do that for the other two vectors as well. Then one other thing to do. Let's look at the problem of solving linear solving a system of linear equations, right? So let's do so B is a column vector of 3 ones. Okay, and then so we want to let's try and solve the equation that bx equals b. So we're going to do okay. So notice here I've put in a hash mark. That's the comment mark, and we've not done that so far, but yeah, anything after the hash gets ignored. So we just put that in a comment to sort of explain what we're doing here. So we're solving the equation bx equals b using this function la.solve, and then let's print the result. Okay, so we get our answer. This 1.75 minus 0.875, 0.125. Okay, and let's just check we did it right. So remember, so multiply by b by x, we do b at x, and that's 111. And let's just subtract off our b. Okay, so we just get rays of zeros. So indeed, we've succeeded in solving the equation bx equals b. And that will do for this initial tour of the linear algebra stuff.